Okay, so yeah, welcome back, everybody. So today we continue to discuss graphical models. Graphical models, we said, are ways to represent joint probability distribution in a compact way, making some assumptions about independence. And we started this module by discussing Bayesian networks, which are the most general graphical models. And we moved on to discuss hidden Markov models, which are also another sort of directed graphical models. I mentioned in the previous lectures that there is another, graphical models is a large family of models. Even within Bayesian networks, hidden Markov models, we'll see later today, there are extensions. But there's another part of this, a very large part of this family, which is called undirected graphical models. So far we had always direct arrows on the edges. There is another class that is called undirected that we are not going to cover in class, so you don't need to know it, for example, for the problem sets or exams, but it's a very important subset of graphical models. And as I said, introduction to machine learning is, as the name implies, introduction. A lot of these things we discuss can be expanded to a full semester class or even more than that. And graphical models are one of these topics where we actually do have a full semester class. So those who are interested, or those who think this can be useful, can take, of course, that class. And similarly for neural networks, similarly for reinforcement learning, similarly for other things that we'll discuss. There's a limit on how much we can cover, but you should know, at least be aware that these exist. But as I said, we are talking about direct graphical models, and within that, we are discussing specifically hidden Markov models. And we ended the last lecture, or in the previous lecture, we discussed inference in hidden Markov models, and the good news was that because of the very strong assumption that hidden Markov model makes, and that hopefully is clear, it's not just that somehow we are better at coming up with algorithms for HMMs compared to Bayesian networks. It's really because of this very strong assumption about the fact that anything after some state is only dependent on that state if we know it, as independent of anything that happened before that state. Okay, so a state can work as a buffer between the information after it and before it. That's only. We said already, I showed an example where this is not true, but this is the assumption we make. If we make this assumption, then inference becomes possible. In fact, inference for most of the questions that we showed is polynomial in the number of states and in the number of observations. Unlike Bayesian networks, where we actually showed or proved that inference is NP-hard. So in hidden Markov models, inference is doable. So the next thing we said is, if inference can be done, what about learning? So, right, hidden Markov models, as I mentioned, has 3 different types of parameters. It has a lot of parameters, but 3 different types: initial probabilities, which we denote by pi; transition probabilities, these are the transitions between the 2 states, between every pair of states; and emission probabilities, which are the observations, or the probability of an observation given a state. And each of these parameters has to be learned from data. And the question is, how should we, or how could we learn these parameters from the data? And we started to answer that. So this is something we started with. And we started to answer this in the last lecture. And we said that if we knew the set of states, so we see, the way we do learning, as we said, is we get observations and we want to learn parameters. That's what we did in MLE. That's what we did in all the classifiers, right? We had training data with labels. In this case, there's no labels, there's just observations. But for example, MLE, right? We want to learn distributions. We see observations, we learn the model. So in this case, the model is very well defined, right? We know that we have, let's say, 2 states. We know that we need parameters for transition, for emission. And if we have known what are the states for each observation, so we get the observation. Had we known the set of states, we said already that learning the parameters would become very simple. Basically, it's an MLE problem, because if we know the states, then initial probability is the maximum likelihood on, what is the first state in each of the sets that we have. Just count, right, and get the probabilities. Similarly, transition probabilities become counts. And emission probability, again, it depends on the model. In the die example, it's a multivariate, it's a multinomial distribution. If we look at, for example, at robots, And when we have sensors and we believe that distances are Gaussian, then the model is a Gaussian. So we know for each state, we know, if we know the state, we know exactly where it is. So we know the real distance, we can get the observation from the robot camera, and we can compute, for example, distributions on the error, right? Like how far is the observation from the. So I mean, the parameters for the emission really depends on the model. But again, they can, if we know the state, they can be learned using maximum likelihood. Okay, and again, we derived this, right, for the initial probabilities. We said it just count how many times you see A as the first state divided by the number of times you see A and B as the first state. Transition probability is the same. How many times we saw A going to B divided by how many times we saw A total or A going to A and A going to B, which are the two options. And emission probabilities for this multinomial is the same. Unfortunately, of course, we do not observe the state. We only observe the values, right? In the dice, we get the values of 1, 2, 3, 1, and so forth. However, as I said, if we had observed the state, we would be easily, or it would be very easy for us to find the parameters. On the other hand, and this is the key point of this lecture, on the other hand, if we knew the parameters, as we discussed in the previous lecture, we can find the states. That's the inference thing, right? If I tell you what are the parameters and you have all the observations, we did the inference. What's the most likely set of states? What's the most likely state at each time point and so forth? These are things that we can determine. Again, I mean, we still need to do some work here and we will do it in the next few slides. But generally speaking, if we knew the parameters, we can use inference to determine the set of states. That should remind you of an algorithm that you discussed before for GMM, which is called EM, expectation maximization. And expectation maximization is a very general approach where we iterate between two steps. In the E step, we basically fill in the missing values by looking at expectation of probabilities. And again, we'll discuss exactly how to do it for hidden Markov models. But again, this is a general approach. So in the GMMs, for example, the expected value we look for is membership, right? Class membership, that's what we're doing. And in the M step, we compute a maximum likelihood estimation. So in HMMs, for example, this is the emission probability, transition, initial, and so forth. In Gaussian mixtures or in clustering, it's the mean and variance for specific clusters, right? But again, this is a general approach where you have two steps, E step, where you compute the M step, and you can show, and this is why EM works, you can show that EM is guaranteed to increase the likelihood of the data. So if that's the case, then EM is guaranteed to converge. We don't know how long it will take, but it's guaranteed to converge because likelihood is bounded from above, right? The likelihood cannot be more than 1. So if we know that in each step EM, and of course the steps can be very long, we didn't say how much each step increases the likelihood, but you are guaranteed that each step, the likelihood can only go up. Now, usually in EM, what we do is because how do you know when to stop? You stop when the likelihood doesn't change anymore, right? So you can compute the likelihood and see that it doesn't change, then you stop. Okay, so you have a stopping criteria as well. But regardless of the stopping criteria, EM is an iterative process. It's not like you do 1E, 1M, and you're done. You iterate between EM. And again, we'll talk exactly about how to do this. I'm mentioning this because you already saw EM as an algorithm. This is another application of EM, which is similar to other things like MLE we used all throughout the class. So MLE is a general method, we apply it differently. Similarly, AM is something that we're using here, and we're using Gaussian mixtures, and we actually use it in many other cases. Okay, so the basic idea of EM is we have an E step where we fill in the missing values. We basically compute expectation for the missing values. As I said, in hidden Markov model, the missing values are the states that we are at each time point, right? So we see an observation at the third time point, and the missing information for us is what state generated this observation. And the M step is about MLE, and MLE is learning the parameters of this of the model, right? So okay, so this sounds like a good idea, and also it's not just a good idea because it's also a doable thing, because we already talked about in the first few slides of this lecture about if we knew the states, how to learn MLE. That's very easy. And in the previous lecture, we talked about inference. So if we know the parameters, we can actually find out the state. However, we didn't do, or we didn't fully, or the inference that we discussed last time does not fully address the things that we need in order to compute the parameter, the expected values for EM. For example, in the previous lecture, we did not discuss, although that's important for learning expectations, right? So if you think about the expectations, we want to know what's the probability of, let's say, ST equals I, right? So that at time t we are at state I, conditioned on all of the observation, not just the observation up to I, but also the observation after I, right? Because all of these observations, even observation after the state, can tell us something. It's true that if we know the state, we are independent. But if we do not know the states, we want to know what's the probability of the states, we have to condition on all of the observations, right? This is not something we know how to compute. We know how to compute it for for the last state. That's something we did. So ST equals I conditional, right? We know how to compute it for the last state, but we don't know, or we didn't derive how to compute it for all states in the middle, right? So for example, just an arbitrary state in the middle when we condition on all of the observations. Again, the important thing here is that we condition on all the observation, not just observation up to t, but also observation after t. Up to t we did already, but this is something we haven't computed yet. But it's important because if I want to know what is the expected or what is the state at time at t, then I need to condition on all the observations. It's not enough to condition on a subset of. So this is something we want to compute. Another thing we would, so this is important, right? Because we want to compute emission probability, for example. How do we compute emission probability? We have to know what state we are at each time point. So for that, we need to know what's the probability of being in state. So that's one thing, and I'll show you how we use it. But there's another thing we need to compute, and that's actually important. So if you have two consecutive time points, okay, this is something we also need. This is something we also need to compute because this is the expectation of a pair of states, and this is important for us because we need it to compute that transition probability, right? The transition probability is basically summing up on pairs of states and then dividing by the total number. However, it's important, and again, I'm not going to show. I mean, I'm going to show you how to derive this, but you have to realize that this thing here is not the same. This is not the same as P of ST condition equals I condition on O1 to OT times P of okay, these two are not independent, even if we have all the observations. So this is, so even though we know how to compute this, we don't know how to compute, or it's not necessarily the case that we know how to compute this. So we need to compute both of these. Or these are two expectations or probabilities that we need to compute. But if we believe that we need to compute that, then the only thing that is left is how to compute it and using the inference methods that we learned. So now we are going to discuss how to compute these two quantities that are really the only thing missing for us in order to use EM for learning the parameters of the hidden Markov models. Okay, Okay, so we already defined alpha I. Remember in the previous lecture, we defined alpha I as the probability of O1, OT, and QT equals SI, where T is the last value, right? You can see here, that's the same. So we use the same. And this is something we discussed and we talked about how to compute. I'm going to define another parameter, which I call beta T of I. Beta T of I is something we call backward. So all of these are forward-looking parameters because they go from O1 to OT. Right, from 1 to T. This is forward, going forward. Beta is a backward parameter. It goes from the last observation to 1 plus T, basically. Just the definition. Again, I can define whatever I want. But basically, beta Ti is P of OT plus 1 to OT, condition on ST equals I. Just the definition, okay? So again, all the observations after T, condition on the state at time T. Just the definition. I can define that. Now, I'm not going to show you, but you may want to derive it yourself. We can derive beta T of I using the induction. I'm not going to show you, but it turns out that beta T of I, and it's basically the same way we did alpha T of I. But instead of starting from 1, we start from T. Other than that, it's the same. And beta T of I can be computed using the same ideas that we used for the alpha T of I, in polynomial time. That's the key important thing. And basically, we have this function here, which is basically beta T plus 1 of J. So we start computing beta T not from 1, but we start from big T and we go down to 1. Okay, unlike alpha, which we go from 1 to. So we start from big T. Big T is the base case. You can show that you can compute it for all I using the definition, and then assume that you computed it for T plus 1 and you compute it for T. Okay, so this is the function. So again, bottom line, I'm not going to show you, but you can try and do it. We can compute beta T of I in polynomial time. Okay, good. I mean, but why do we care about this? Well, we care about this because once we have alpha and beta T defined, we can answer the first expectation or first probability issue that I mentioned, right? And this is computing the probability that we are at state I at time T, condition on all the observations. Right, that's the first expectation I told you we need to compute because this is required for the emission probability. I want to know which state I'm at time T because I see an observation and I want to know how many observations came from state A, from state B, and so forth. So I need to know what state I am when I see this observation. So this is something we want to compute. And the claim is that this is alpha T of I times beta T of I divided by sum over alpha T of J, beta T of J. Why is that? Well, I'm saying that basically, right? So we can treat it as P of A given B equals P of A and B divided by P of B. So this is A, this is B. So we are saying that alpha T of I, beta T of I is basically an end of O1 to OT and QT equals SI. Why is that the case? Because we can use the chain rule, right? So we start with this. We divide it into two parts. One is the alpha T, which is O1 to OT and QT equals SI. And the second is OT plus 1 to OT, condition on QT and the other alpha to OT. But once we have QT in the condition, these drop. We don't care about them if we know the state at time T. So this becomes alpha T of I times beta T of I. And again, this is, I'm not showing it, I'm not writing it, but hopefully all of you should, based on what I'm explaining, be able to derive this. So basically, P of A and B, which is the numerator, is just this. What about the denominator? Well, P of O1 to OT is just a sum. We can use the sum rule of P of O1 OT and QT equals SI. And we just said that, right, for I, this is alpha Ti, beta Ti. So if we sum over all of them, we basically get P of O1 to OT. We have other ways to represent O1 of OT, right? We already said we can represent it using alpha and so forth, but just using alpha and beta is another way. Okay, so basically, if we believe the numerator or basically the joint of QT equals SI and O1 to OT is alpha Ti, beta Ti, then the probability of O is just the summation of all of them, and basically. Okay, the important thing, and again, I mean, you can try and derive it later, and you should be able to derive it based on what we did in the last lecture, and based on simple probability laws. The important thing is that using this, we can use alpha and beta, which we know how to compute in polynomial time, to compute the expected value for state I at time t, which we define as STI, probability that we are at state I at time t.
Siv, there's a question in chat. Someone is saying that you said that OT is the base case. What do you mean by that?
No, OT, I mean, okay, good. I didn't mean that OT is the base case. OT is observed. And what I meant is that, oops. So to compute beta T of I, we start with computing beta big T of I, right? The definition of beta big T of I, and this is the base case, is basically right, it's P of O, well, T plus 1 up to OT, condition on QT equals, so basically, where did it go? Okay. Right, so beta T of I equals basically, we set it to 1, okay, or we just have a base case there. And then beta T minus 1 of I is beta is P of, let's see, P of O T condition on Q T minus 1 equals 1. Right, and now basically what you need, again, I'm not, so this is the base, and then you really need to, this is equal to sum over P of O T Q T equals J, sum over J, conditional Q T minus 1. Equals I. So basically, this is how you do the induction. So you start from the base, and then you go down, and you do the summation like we did before. Again, I don't want to do the derivation, but you can try it and see that it works. Yeah, so I didn't mean that OT is the base. I meant that big T is the base. We start with the last one and go down rather than starting from one. Okay, so this is the, oh, sorry. So this is the first value we compute. The second value, so we already computed this, right? The second thing we need to compute is P of QT equals SI, QT plus 1 equals SJ, which is this transition for a pair condition on all the observation. I already said that this is not the same as just the product of QT equals SI condition on O1 to OT and QT plus 1. It's not. But it's not so hard to derive this. Again, basically, the way to derive it is the same as we did before. So you do P of A and B divided by P of B. The denominator is the same because it's P of O, so it's basically going to be the same. This one, you need to break it slightly more because now you have these two, so you need to include the transition probability, which is why it's not the same. So you need to include the transition probability and the emission of the value at time in this case time t+1. But other than that, it's basically the same. Okay, so again, you can try and do the so to do this, you just again you use just the chain of P of A and B equals P of A given B times P of B. So again, the important thing is that we can use alpha and beta. Basically, you can use the simple inference methods we derived, which are polynomial time or take polynomial time, to get both ST of I and ST of ij. These are not, or we cannot get ST of ij directly from ST of I, but we can get it from alpha and beta. And then if we have that, then we basically have the expected value, right, for being in state I at time t, and the expected value of transitioning from state I to state j at time t. Okay, these are the two expectations or the two probabilities we compute. And again, this is done assuming, of course, that we know the parameters. We needed the parameters, the emission, the transition, because we needed, first of all, to compute this, but also for the alpha and beta, they rely on that, of course, okay? So obviously we need the inference, but it's slightly different than the inference that we did before, because now, unlike before, we condition on all the observations for intermediate states, not at the last point, which was what we were interested in before, but now, but we can do that, that's not so hard. And maybe I'll ask you soon a question that yeah, you'll play with it. Okay, so that's the E step basically. In the E step, the two probabilities we compute is ST of I and ST of ij. That's the only thing we need to compute. Okay, and as I said, these ST of I we need in order to compute, you will see in a second, the emission probability. And also we needed to compute the initial probability. What's the probability of starting in state A? Because that's only a function of one state, right? Because we start in a single state. ST of ij is something that we will use to compute parameters for the transition. And let's see how we do that. So this is the M step. The M step, we need to compute several probabilities. The first one, we are going to compute the emission probability. To compute the emission probability, so basically we want to know what is the probability of seeing 1 if we are in state A. What is the probability of seeing 2 if we are in state A, right? For each state, we need to compute the probability. How do we do that? We need to find all the observations in which we are at state A, but we don't know what they are, right? So we take the expected value we computed, which is ST of K for each state, but only for those states that the value is let's say 1. So let's say I want to know what's the probability that if I'm in state A, in die A, I output 1. I go into all of the observations that I'm in state A, and I sum how many of those, I go into all the observations where I have 1, and for each one I know what's the probability that I'm in A, right? So this is the observations, the times where I see 1, and this is the probability that I'm in state A in that observation, and then I have to divide it by all the times I've been in state A. How do I know how all the times? If any observation I can be in state A. So I have to sum basically on all of the possible time points. For each one, I have a probability of being in state A, or you can think of it as the summation, right? Because this is, so basically each of these sums a different set of time points, right? So this, if J is 1, we sum all the time points when we saw 1. If J is 2, we sum all the time points we saw 2, and so forth. So together we sum, if we sum over this, we sum on all the observations, basically all the time points. So this is the sum of probabilities that we were in A, and this is the fraction of those that we saw 1 when we were in A. Okay. So this again, this is just, I mean, basically it's an MAD, right? It's counting how many times I saw A and 1 and how many times I saw A. But this time we use fractions or expectations because we don't know that now. But anyway, once we know how to compute ST, this should be basically, once we know the probability for being in state K at time T, that's how we can use it to compute the emission probability. Transition probabilities, same idea, right? Transition probabilities, we said we look at all the times that we were in A, and ask how many times we were in A in time t and in A in time t plus 1. This is the number of times we move from A to A. And how many times we were in A at time t and move to B in time t plus 1. This is the number of times. So for this, again, we don't know, but we already computed ST of ij, right? So we computed the probabilities of being in state I at time t and state j at time t plus 1. So I can sum up for each pair of states, right? Let's say A and B, okay? Or A and A. J can be A as well, right? Because This is transitioning from A to A, from A to B, from B to A, and so forth. So I can sum up all the times that I saw this pair, right? If I sum over for A, if I sum over all the other states that can be after it, then I sum over all the appearances of A, because something has to be after A, right? So basically the denominator is summing over all the pairs, which is basically, in this case, K is two states. So K is A and B, so AA and AB. This is all the time, so this is the denominator. And the numerator is the times out of those, how many times did I see AA, for example. So again, maximum likelihood estimation count, but using not the actual values because we don't observe them, but the expectation or probabilities for this. So again, once we know how to do the inference or once we know how to compute the probabilities, this is straightforward. So this is the algorithm. So basically, we start with a set of observations. We have a number of states which are defined. It's very important that we need to guess something. We cannot start, right? We either guess the parameters or we guess the states, but we need to guess because EM basically, E assumes M and M assumes E. You cannot start from nothing. Usually we guess the parameters just because we can easily just say the parameters are uniform, or maybe it's harder to guess the state. So we guess some parameters basically. Again, the guess could be uniform. So the probability of 1, 2, 3, 4 is 1/6 or something. And then you compute the E step. If you have the parameters, you can compute, you do the inference, you compute the M step, and then you ask whether things converge. Converge, we said, is computing the likelihood, right? What is the likelihood? How do we compute the likelihood? Anybody can tell me? What is the likelihood of the model? So I said convergence, right? So we need to compute the likelihood of the model. And then if it's, we said it can only increase, it can never decrease, but it might stall. So we get to a local minima. So EM, by the way, is not guaranteed to get to global optima, but it's going to get to a local optima. Basically, it can stop increasing. So how do we know that it stops increasing? We look at the likelihood, and if the likelihood doesn't change, we stop. Because if 2 iterations, the likelihood stay the same, it will stay the same forever. Because the parameters are the same. Then if they didn't change between 2 iterations, they're not going to change anymore because these are the maximum likelihood estimation parameters. So what is the likelihood? How would you define the likelihood of the data? Give me any, yeah, exactly. So someone says exactly. So the likelihood is P of O, or P of O1 to OT, which of course is condition on all the parameters. We don't say it, but yeah, the likelihood, and this is something we compute anyway. So this is something that is easy to compute, easy to compare, and we stop when it doesn't change. Good, thank you. Okay, so this is EM for Markov models. Yeah, one small point I didn't mention, but that's really easy. So I didn't mention the initial probability, but it's the same, right? If we have multiple sequences, then we just count how many times we believe that the first one is A, how many times we believe the first one is B, and divide, and that's the, because we have, again, rather than using ST, we use S1 of A, S1 of B, and for all of them. Okay, so this is hidden Markov models. This is learning we finished inference and learning in hidden Markov models. Again, both of these can be done very efficiently in polynomial times, which is why hidden Markov models are very popular, unlike Bayesian networks. There's a lot of applications that use hidden Markov models. As I mentioned initially, hidden Markov models were developed for the speech processing community. But since then, they have penetrated or being used by a lot of sequence-based domains, image, movie analysis. This is an example of using HMMs for biology. So in biology, and again, I always say my area is computational biology, but nobody in this class is expected or assumed to know anything about biology. If you do, great. If you don't, that's not a problem. It's not, but some of the examples that I give are from biology, but it's not critical. If you don't understand the exact meaning, that's fine. I mean, as long as you understand it. So I don't expect anybody to understand biology for this class. But anyway, one very important issue in biology is if you find a new protein. So we get new organisms all the time. Actually, there are people who go to the ocean They take these big fishing nets, they get a lot of organisms very small, and they sequence them. Sequence means they read their DNA. And when you read an organism's DNA, you can identify new proteins. Proteins are the machines that work in our body. They are very important. Some proteins are very useful, for example, for combating diseases. So there are proteins that are used to as medicine, and we know that, for example, right, antibiotics is something that are based on proteins that some of the bacteria themselves express to fight other bacteria, for example. So the knowledge of what proteins are and which proteins we have is very important, and it's very exciting if we find new proteins. It's very unusual because we know already a lot about proteins, but now how do we know if we find a new protein? We should compare it to all the other proteins we already have. So there is a big database of proteins. However, comparing, there's millions and millions of these proteins that are very similar. So comparing them is very hard. So one way people use in order to decide if what this protein is or which family is to define proteins using hidden Markov models. So basically, they have a hidden Markov model for different families of proteins. And when a new protein comes in, they score it using the model. And if it scores very low on all the models, it's likely a new protein. But the question is, how do you learn a hidden Markov model for a protein family? So a protein, in this case, I'm representing it by DNA, it doesn't matter, it's just a collection of letters, in this case, A, C, G, and T. However, they don't have to be exactly the same. So for example, there could be cases where, most of them have A, but some of them have T. Other places, most of them have A and some have C, and some of them have some missing values here, but others don't. So the idea is that if I give you some proteins that I manually curated and told you that I belong to the same family, how do you build an HMM from that? How do you learn parameters that now you can apply to new proteins to decide whether they belong to you? And this is the HMM that people use. This is called profile HMM. It's something that is very common or commonly used in the biology community, where here you have what's known as the consensus site. So these are the actual letters. These are called deletions. So these are places where some proteins don't have any value, but others may have. And these are called insertions. So this is the other way around. So a protein can start here, have an insertion that other proteins don't, and then go here, or it can have, sorry, this is the deletion. So it has a deletion, so it doesn't have this and others have, or it can have an insertion. So things that others don't, and so forth. And this is an example of an HMM. Again, the details are not important. The important thing is that this can be used. So this is an example of an HMM. So each of these is a state. This is the learned HMM already. So each of these is a state. Inside, you see the emission probabilities. So this is the probability of seeing A in the first, and this is the transition probabilities. So if you see, if you start in this state, you are guaranteed to move here. But here, some of these sequences have an insertion with probability 60%, and some go directly to the next match state. And again, this is the model that we learned from the data, but you can see the model has emission probabilities. We start here, so the initial is easy. It has emission probabilities, transition probabilities, and all the other things. Again, this is a very simple example, but in practice, protein sequences are much longer and more complicated. They actually have 20 different letters, not 4, and the models can be more complicated. But in practice, this is something that is being used quite a lot, and it's sometimes much faster than just doing a simple comparison to a database, especially when the number of sequences is very large. So a hidden Markov model can represent tens of thousands of proteins in one simple model, whereas if you just do database search, you have to look at all 10,000. Okay, good. So this is it for HMMs. I do want to talk a bit about or some extensions to HMMs, which are actually very useful. So HMMs themselves are powerful, but they don't solve all the problems. And I want to show you several cases where HMMs on their own don't solve the problem, but simple extensions to HMMs, which are simple to define, not always simple to derive, can actually solve the problem. But before we do that, let me ask you a question. So I turn to the poll, and I'm releasing a poll about this is inference learning in HMMs. So I released HMM3. You should look at it. And yeah, this is a bit more involved. I have to say this is, again, so obviously the polls or the quizzes are not graded and so forth. This question is actually harder than usual. I warn you, so take a bit, maybe a bit longer. It's very similar. In fact, it could be, I don't remember, it could be an exam question. So if it was an exam question, it's likely wasn't the only question on HMM in that exam, but it's actually at the level of exam questions that we ask. Yeah, so take a look and we will solve it a bit more carefully than we usually do. But just again, to clarify that the probability that I'm showing here is not what we learned in class. In class, we did P of QT equals SI condition on O1 to OT. This is the other way around, and it's completely different. I mean, don't assume that, right? I mean, hopefully I don't want you to get confused. So this is a definition. I'm not asking you to derive this, right? If you look at the question, I'm asking you to use this. So you don't need to derive it, but make sure you understand that it's not the same as what we learned in class. Very different creature. And you don't need to derive it. You just assume that we can compute it. That's it for this question. So Daniel, students can't see the votes, right? Only I can see them, or you, or they can see them as well.
It depends how you set it up, but I don't think they can see their vote.
Good. Because so far, from the votes that I already have, this is a very hard problem. Which
I think it's a hard problem, so no one should feel bad.
Yeah. Yeah. No, it's a hard problem. And again, I always say, I mean, these things it takes some time to digest, even if you don't get it right in the poll. That's not a problem as long as you take the time to look afterwards and understand what was. And there's similar questions, I would say, in previous exams. So if you don't get it right, you will have a chance to practice with others. But, you know, yeah. So I don't want to rush you because this should take time, but we do need to move on. So maybe like another minute, a minute and a half, and just try and solve it for those who haven't. Try to do it. Yeah, 10 seconds for those who haven't done it, then we will solve it. So yeah, so this is the distribution of answers. Big disagreement here between, I don't know if you can, I think you can see my screen. So big disagreement. Which means that, again, this is not a simple question. So let's do it. And again, try to see the main thing we were looking for when asking this question. Not so much, I mean, I care less about the details, more about the thinking process. So if you think about this question, what we gave you is basically P of O, which is the observation condition on QT equals SI, right? This is the function that you get. And what I asked you to compute using this is P of O, right? That's the O up to 200, but this is basically, in our notations, that's what I'm asking you to compute. How can we go from this to this? Well, we know this is the summation, right? So basically, P of O equals sum over I, P of O and QT equals SI, right? That's the summation, we did it several times, which equals to sum over I, P of O given QT equals SI, P of QT. Okay, so this is, we haven't used anything, we just derived one way to use. Now, you are allowed to use, in this case, P of O given QT equals SI for I equals 1. You're not given it for 2 and 3. So you would have to, whatever T, so T has to be the same, right? Whatever T is, you have to compute the probability of being there. if you think about it, so I only gave you two options, I think, in the question, or maybe, let's see how many options did I give you. Yeah, I only gave you two options, 2 and 200, right? That's the two values that I gave you. If you think about it, it's much easier to compute the probability of being in a state at time 2 than in being at state in time 200. Because 200, you have to say, you know, what if I transitions? When did I transition here? Did I stay? I mean, maybe it's possible to compute that. But let's look at what happens when we use t equals 2. So for state 1, P of O QT equals SI is, by definition, right? This is a V, how do we call it? VS12. Right? This is VS12, right? This thing here. What's the probability that we are in state 2 at time 2? It's only if we stay there. So this is times half. So this is for state 1, right? So this is what we have here, which is VS12 times half. Okay. Okay, so this was for state 1. What about state 2? What's the probability that we are at time 2 at state 2? So the probability that we are at time 2 at state 2, where does it go each time? Right, so this is point, right, it's 0.25, so it's half to the power of 3, right? And what is the probability of observing A's if we are at, if we know that at time 2 we are at state 2? Then the probability is the following. If we know that at time 2 we are at state 2, we had to be in time 1 and status 1. There's no way. We start there. And then we move to state 2, and then basically, so it's 0.5 all the way, right? So it's basically half to the power of 200, if that's the case. So for this, if this is state 2, it's half to the power of 200. So this is half to the power of 3, sorry, half to the power of 2, right? Half to the power of 2, so we get half to the power of 202, okay? So this is the second component here. So it's half to the power of 2 times half to the power of 200, which is half to the power of 202. And the last thing is state 3. So for state 3, what is the probability that we are in state 3 at time 2? It's the same, right? It's half to the power of 2. It's 0.25, so it's half to the power of 2. And if we saw, if we are in state 3 at time 2, what is the probability that we see all A's? Well, from 2 on, it has to be A. And for the first one, it's half, right? So it's basically half times half to the power of 2, which is half to the power of 3. So combining everything, we get to a half over V of S12, half to 2 to the power of 2 to S2, and half to the power of 3 for S3. And this is the solution. Okay, again, if you use 200, you may actually have been able to get some value, but it's very hard to know what is the probability of, for example, of seeing A if you are at state 3 at time 200, because it depends on when we move to state 3. If you know that you're in state 3 at time 2, it's very easy because you had to move at time 2. So the idea here is that, right, once you open this or do the summation, it's hopefully clear that you need to find a time point where it's easy to compute these values, except for state 1, where it's hard to compute, but we don't require that you compute it. Okay, so this is given to you. Okay, so this is the solution. The solution in this case is 2, which again is not trivial and requires some work. In this case, it would be better not to look at the solutions and then see which one is correct, but actually to write the derivation and see which one works. But that's not always. Sometimes it's better to look at the solution than choose. But this is, I would say, pretty common question. The nice thing about these questions is that, unlike some complaints, we have the very clear quantitative answer. It's not, right? There's one number or one function that you have to choose. So we like it in exams. And I think it does test at least some of understanding, and definitely it's based on things we did in class. So it's not, something we assume you should know, but you never saw before. Again, if you didn't get it correct in the poll or didn't even think about it, that's not a problem at all, because we just learned it and it takes time to absorb. But go over this after the lecture, see that you are comfortable with it and understand the rationale and
Ziv, there's a question here. Someone's asking if you could explain why to derive P of O, we only need to derive, we only need the V of state 2, time 2.
No, I didn't say that. So let's see if I have it.
V of S1, 2.
No, I didn't say that. So to derive P of O, you need to sum over all states, and you need to compute P of O and all the states. So you need to have the sum over all the states. So SI here is 1, 2, and 3. I just said that computing this for 2 and 3 is very easy. Computing this for 1 is hard. So computing QT equals S1 is easy. Computing O or AAA, if we are at time 2 at state A, at state 1 is not trivial, but you don't need to compute it because this is the function I gave you. So I didn't say that you can, in fact, you cannot ignore the other states, but finding the value when for that state, if you use T, so you have to choose T, right? If you use T equals 2, then finding these values of O condition on, we are in state 2 at time 2 or state 3 at time 2 is very easy. That's what we derived. It's either half or half to the power of 200. It's very hard actually to do it if we know that we are in state 1, but you don't need to do it because that's the value that I gave you, this big thing. So absolutely, you cannot ignore the other states. And again, this is true for all of this is true for any HMM. This function here does not use the structure at all. This is just the chain rule, right? That P of O is the summation rule, right? P of O is sum over I, this thing here, right? This is something we did all the time. Sum over I, P of O, and QT equals SI, because we have to be a time T in one of the states, right? So this has to sum to 1 over O. And again, this type of thing, or this type of summation, marginalization we are doing all the time. So hopefully this is good. Okay, any other question? Okay, good. So as I said, this is this is similar to some questions we had in exams. I'm not saying we'll have the same ones, but this is something you should get comfortable with, and there's a lot of examples in the exams that we shared with you that you should look at. Okay, so next, I want to talk about, as I said, some extensions of hidden Markov models that can address or can solve problems that hidden Markov models on their own cannot solve. Yes. So someone raised their hand. Yeah.
Hi, Professor. I just want to quickly make sure that the reason that you choose time equals to 2 is basically for an easier computation.
Right. So if you look at the solutions, you're only allowed to use time. I think there is a limited number of options, right? It's not like you can use any. Maybe time equals 1 would be better, because if time equals 1, you can just, but you're not allowed to use it. So if you look at the solution, you can either use 200 or 2. Okay. I'm not saying that 2 is the easiest. I'm just saying out of the options that we have, 2 is the only one that we can easily use. Right, 200 would be very hard to compute. So yes.
Okay.
But I'm not saying 2 is the, I mean, honestly, if someone gave you 1, it would have been the best because you already know, right? At state 1, we know exactly what the state is, so we don't even have to have a probability there, and we are done, basically. But unfortunately, they didn't give it to us as an option. So we had to choose.
Okay. Thank you.
Okay, so let's talk about 3 extensions. One is called, of HMMs. One is called factorial HMM. One is called input-output HMM. And the last one is called dynamic Bayesian networks, which is basically some type of almost a hybrid between HMMs and Bayesian networks. So let's start with factorial HMMs. Let's say we have a robot, which we discussed quite a lot. He's moving in the environment, maybe in gates, which is, usually it's easy for me to discuss gates because most people take this class have offices in gates, or at least have been to gates. Nowadays, maybe most of you have never been to gates, but hopefully this will change soon. But gates is basically the computer science building. So let's say we have a robot that is moving in gates and it has a HMM model. And in fact, we used to have it. It's a robot that is a tour guide. So it picks up people next to the elevator and tries to give them a tour of gates. And people who have a lot of patience can do that. I'm not sure I would recommend it to anybody. But anyway, let's say you're designing this robot. And this robot, of course, it has to know where it's going. So it might have some HMM model about, it can look at the distances and stuff, but it can have an HMM model to determine where it is using sensors and stuff like that. But in addition, it has other things, right? So the emissions, the observations are the distances, but also the robot speaks in different languages, which is also an emission. So depending on the tourist, the robot can decide whether to use English, Spanish, or French. And also maybe some tourists just want the robot to walk. They don't want to hear anything. And so there is a lot of possible emissions. However, you can see that even though the robot is doing all of these things, it's sending sensor information to know where it is, it's speaking, it's deciding whether to listen or not. These are decoupled, right? The fact that you're in a specific location shouldn't affect whether you speak Spanish or English or something else. And the fact that you speak English doesn't mean that you're in a specific location. But still, given a state, the emission probabilities would couple all of these together. We'll couple the language that you're using, the location that you are, and whether you're talking or not. So in some sense, the emissions, even though they are all coming from the same state, they are not really the same. And that makes it a problem if we want to design HMMs, because if we did need to couple them, then the number of parameters is going to be very large. Because, right, we have a K by K grid, each one has 3 different languages and 2 different options, so it's 2 times 3 times whatever the grid is, whereas in practice, we only need, these are independent things, right? So rather than designing an HMM where each state is a combination of all of them, the question is, can we design an HMM, which is called factorial HMM, where each state is a combination of different, or basically each state is controlled by a different, or each state is a combination of different substates. Right? So basically, we have this vector of attributes, but some of them are completely independent of each other. Now, because of the way we define emissions, we have this multinomial output, but maybe we don't, and then we need a lot of data to learn, but maybe we can learn much easier if we knew this approach. So pictorially, this looks like this, right? So the gray one is the emission, and the empty circles are the states. So we have some states related to language, and if you start speaking English, it's very likely that you will speak English in the next state. This is completely independent of where you are, right? It's, even if you go left, right, up, down, you will still speak English. So we don't need a transition probability from location to language. We just need a transition probability from language to itself. Similarly, location, right? If you speak English or Spanish or French, it doesn't change where you are. So the location should infect itself and others and so forth. All of these should be coupled in the emission, right? Because the observation are basically a function of all of them together. But they are not separate HMMs. Sorry, they're not completely dependent. They are really separate things coming from different. So in some sense, we would like to have an HMM for the language, an HMM for the location, and maybe an HMM for talking or not. So this is called factorial HMM. It's easier because it decouples the transition, right? In terms of transition probabilities, we have to learn, or the number of states we need to define is much smaller, and the transition probabilities is much simpler. However, right, so this is good. The problem is that they are becoming coupled in the observations. So if they are really fully independent, maybe that's easy, but sometimes it's not completely independent. And anyway, when you do the learning, you have to couple them. So basically the M step here is very easy, right? Because the M step, if we know the parameters, we can do inference on each of these, or basically we can find the probabilities. But the E step is very hard because it's not trivial to decouple the states, or it's not, or let's put it this way, it's hard to get a polynomial time algorithm to decouple the states given the observations. Sometimes it's possible, sometimes it's not. It really depends on the model. And usually inference in these models can be exponential, not in the number of time points or states. That's not the major issue, but in the number of factors that we have. So this is, each line here is a factor or something that affects the output. And together they have the emission. Okay, so again, important points to know are that, I mean, this can be solved by an HMM. It's more efficient than regular HMM learning because each state is really a combination of 3 different states that are to some extent independent, but they are coupled when we do the emissions, so inference can still be quite complicated. Okay, so this is called factorial HMMs. Yeah, and you can expand them, right, to represent more than just like any other graphical models, right? So if you assume that things are not completely independent between the factors, you can include that as well. Of course, every time you include more directions or dependencies, the inference of the model becomes more complex. So you need more parameters, obviously, here, and also inference is hard. So this is factorial HMMs. Next is input-output HMMs. So input-output HMMs deal with the problem of sharing information between HMMs. So let's say we have 2 robots, right? Both of them, both of these robots are more or less the same, but they are from different generations, right? Generation A, Generation B, Generation C. And these different robots, because they are different generations, have a slightly different transition probabilities. Not very different, but they might move a little bit faster or a little bit slower because, you know, maybe the motors is slightly better, or I don't know. So now, if we have 2 robots from 2 different generations, we can learn 2 different HMMs from them, right? Because the transition probability is different for these 2. However, a lot of the things are shared. For example, emission probabilities, the sensors are more or less the same for these robots. So if they're in a specific location, they will see the same thing. But the transition. So the question is, can we share parameters between these different HMMs? And the answer is yes. Right? So basically, all the robots will share with the same emission probability, but they might differ in the transition probabilities. And in that case, we can use something called input-output HMM, where we encode by R, for example, the model of the robot. So let's say model A, model B, model C. R is not directly affecting emissions. Emissions stay the same. So if you're in a location, the sensors don't change. But the transition probabilities can be a function not just of the previous state, which is what we usually have, but also of R. Okay, so now transition probabilities are not a table anymore, or maybe there are multiple tables. You can also do some other functions. So for example, we used input-output HMMs with a probabilistic transition function, for example, logistic regression. But I mean, there are lots of ways to encode it. The important thing is the transition here is not just a function of the previous state, but also a function of R, of the model encoded in R. And in that case, again, learning becomes a bit harder because now you have to depend not just on previous state, but also on the information encoded. The parameters may change because you might have multiple transition matrices. So you might have not a matrix, but a cube, depending on the model, right? So for this model, you have this transition probability table for this model. But on the other hand, you can still show parameters, for example, for the emission probabilities. And again, this could be a function, in which case you share even more parameters between them. So the impact between different transitions could be similar. So this is called input-output HMM. Again, this can be further extended by making the inputs themselves be time points and so forth. And you can, right, you can have also the model affect the emissions, but I mean, this is the most common case. And you can have multiple inputs. So this is input output. And again, these mainly deal with sharing parameters between different models. The last part is basically extending Bayesian networks to take time into account. So we already said that the major problem in Bayesian networks, which is why we are using hidden Markov models, is the fact that they do not contain self-loops, okay? So let's say I would like to predict the price of Google's stock today, and I can access the price of all the other stocks from today and from yesterday. It doesn't make sense that I don't use the price from yesterday, right? I mean, obviously the price from yesterday has a lot of information. Of course, the price today also has information like Yahoo's price, or Yahoo is not traded, but let's say Netflix or Apple or whatever. I mean, that has a lot of information if I know it today, but the Google price yesterday obviously has a lot of information on the price today, right? I would expect it to be pretty similar. So if I use Bayesian network and I don't allow self-edges, I cannot use it. However, there's something called dynamic Bayesian network, which basically roll Bayesian network over time. And in that case, you are allowed to use self-edges because it's not really the same node. In other words, if we have two slices, this is day 1 and this is day 2, then we can have an edge between Google in day 1 and Google in day 2. From our point of view, this is Google. But from the network point of view, these are two different nodes. So you can see if this is a valid dynamic, this is a valid Bayesian network. So within a specific time point, I don't have a self-edge from Google, but from the previous time point, I do have, right? And I still have edges within a time point and edges between time. This is called dynamic Bayesian networks. Again, this is still a Bayesian network, so it's not a hidden Markov model because we don't assume, for example, that we have observation and emissions. All the values are part of the node. So the Google stock price is the actual value we observe for G. Okay, so it's not we know that Google is G, and no, this is really the observation. So this is still a Bayesian network. The only difference is that we roll it over time. And dynamic Bayesian networks, basically, we represent with two slices, but it doesn't necessarily have to represent just 2 days. Basically, this represents all the value, all the data that we have. So we can get data from 10 different days, and we always use the previous day to predict the next day. So we can learn it from 10 days, from 20 days, by dividing it into pairs. So we assume this is called stationary. We assume that the dependencies over time are the same. So if you do it Sunday to Monday, Monday to Tuesday, it's the same. So in that case, we only need to learn 2 slices, right? The slice for the initial time, the first day, and the slice for the second day. And we can do it with a lot of input data, not just from 2 days. We can do it from input data from 10 days, 20 days, 50 days, as long as we take for each time a pair of days, consecutive days, and use it for learning. This is called DBN, very popular and successful in the time series community, because now you can use the same ideas of, I mean, you're not violating Bayesian network. This is still a DAG, but you can model self loops, at least over time. So not Google on the same day, right? In the same day, you can only use, I don't know, some other stocks, but over time you can still use it, which makes a lot of sense because that's information that you want to, or you may want to use. Okay, and again, the probability.
Sorry, what is PA of X here?
What?
What is PA of X here?
Okay, yeah. So this is what we define. So PA of X is the parents, and P of so this is generally I mean this is the joint likelihood here is the probability of Xi condition on the parents of Xi, right? This is like the general likelihood of a Bayesian network. And the important thing is that this is the same. We are still, so the reason I'm writing this is that this is not a hidden Markov model. In hidden Markov model, we have the probability of the transition and the emission probabilities. In this case, we have the probabilities condition on the parent. So this is still a Bayesian network. And you can see that it's a valid Bayesian network, but we do have, or we do allow loops in some sense, just over time. We don't allow them. And this, right, this notation is the notation. You can go back. This is what we used in the Bayesian network lecture. So it's the same. Right, and once you and in terms of learning, once you learn it for 2 time points, you basically roll it out for 3, 4, whatever. Basically, the structure stays the same. You don't assume a different structure beyond. So basically, you assume that's known as stationary. You don't assume dependence. So that's why if you get 4 time points, 5, you can learn from all of them together. The structure stays the same, the values, of course, change over time. So even though we discuss it in the time case like HMMs, this is really a Bayesian network. And again, this is Bayesian network, so it means that inference is NP hard. So I mean, we still have all the problems that we have with Bayesian networks, learning, and so forth. But there are a lot of algorithms that can deal with that, and all of the algorithms we mentioned for Bayesian network will work. Again, the main advantage here is that you can have dependencies for the same variable over time. Okay, so that's it for HMMs. I should say that these three, the factorial, input, output, and dynamic Bayesian network, are not something that we expect you to know for the exam. It's good for general knowledge. It's good to know that we have these things, but you don't need to know. So we didn't talk about any of formal, unlike what we did with HMMs or Bayesian networks, we didn't do any formal derivations. And honestly, I didn't even define them formally. So you don't need to know anything about how to do any derivation or even encode things using them in the exam. We won't ask about them. So if you didn't understand them, or which is likely because I didn't formally, that's fine. Again, these are things that in the graphical models course, of course, we expand on and define more formally. Okay, so that's it for graphical models. Let me say again a few words on the exam. Daniel wrote a very long post that you should read. Exam, we always, and we are still doing it, it's open book, open notes. We don't want you to use the internet. Now, obviously, this is much easier for us to enforce when you are in class. In this case, you will be home with your Zoom. We ask that you open the camera. That's the least we can do, but it's going to be hard for us to really know if you communicate or not. We hope that you don't. I can tell you that this is not the first semester where we did online teaching, and the previous we started right in the middle of the previous semester, and the previous semester went well. I mean, we thought that students behaved very well, and I hope this will continue, and that's my expectation. And people, I mean, yeah, people definitely take it seriously. Other than that, the exam is very similar to what you would have in class. So you will be in rooms, you can ask questions from us, and we will answer. We will post, if we have any corrections, it will be posted in the entire class, and you will have 2 hours. And again, the only thing I encourage you is to do a test run on Gradescope to make sure that it's easy. I don't want you to run into technical problems in the exam. You should have a class or material. I mean, you should run into the exam problems, which are really based on class and understanding. That's the goal of the exam. But we don't want the exam to be, or your performance in the exam to be related to any technical issue. So we really encourage you to give it a test or test the Gradescope before the exam. Make sure that you can easily interact, upload your questions. And again, this worked pretty well in the past, but the more practice, the better in that regard. Yes, and as for questions, yes, we posted a lot of previous exams on the website. I do want to say one thing. Not all the material covered in previous classes have been covered in this class, and definitely not all the material up to a certain point. So if you see questions that, for example, on reinforcement learning, right, on the exam, it doesn't mean that you should know them. We didn't cover reinforcement learning, so not expected. And sometimes it's not, and sometimes people go into different, like for example, in neural network, people can talk about different things that we haven't covered. So if you see things that don't look clear or maybe not familiar, that's fine. I mean, different, even though most of the classes cover most of the same material, there is differences. So it could be that there are questions that you cannot answer because we didn't cover them. And the goal would be to cover or to have in the exam only questions related to what we talked about in class. And that's it. Yeah. As Daniel noted, I'm going to host a review session next Saturday afternoon. I always debate whether to do it, but I find out that people don't really start learning until very late, so I usually do it a day or two before the exam. That's why I'm doing it on Saturday. Yeah, and that's it. So I'll see everybody next. We'll see everybody next week. Bye.
All right.